All right, so let's continue our discussion on section 5.7. So we have these theorems for the derivative of inverse sine or arc sine, arc cosine, arc tangent, arc secant, arc cosecant, arc cotangent. And notice that the derivative of arc sine, 1 over square root of 1 minus x squared. The derivative of arc cosine looks exactly the same with a minus sign. Derivative of arc tangent, 1 over 1 plus x squared. Derivative of arc cotangent, the cos have a minus sign, so it's minus 1 over 1 plus x squared. And then if you know the derivative of arc secant is 1 over x times the square root of x squared minus 1. So here I put that in red because these flip, but it also has an x factor in the bottom. The derivative of arc cosecant also is the same thing as derivative of arc secant, except the minus sign on top. So anyway, we have these derivatives here. So really we need to know 3 of them to know all of them. Okay, and just recognize the pattern there. So now let's do a couple of things. We're going to do look at an example with number 7 here. Number 7 says that x equals arc sine of 1/3. So if I do that, then we're going to ask different questions like what is the cosine of x, what is tangent of x, things of that nature. So basically I'm going to draw a picture here. This is true if and only if I take the sine of both sides, then I can take the sine of x on the left, and then the sine of the arc sine is going to undo each other. So this is true if and only if the sine of x equals 1/3. What I could simply do is draw my angle x there on a right triangle. Sine is opposite over hypotenuse, so this is 1 for the opposite side, 3 for this side. So then if this is a squared plus 1 squared equals 3 squared, with it, which is Pythagorean's theorem there. So a squared equals 8, so this is going to be the square root of 8, or 2 square root of 2, okay? So once again, we just have a squared plus b squared, which is 1 squared, equals c squared. So a squared plus 1 equals 9. So a squared equals 8. And of course, when we take the square root, it's plus or minus, but this is a distance, so it's the positive one. All right, so cosine. What is cosine? Who had this one? Trev?
Square root of 8 over 3, 2 square root of 2.
Okay, so, but it's, say it in word like, what is it? SOHCAHTOA, right? So this is adjacent over hypotenuse. So the adjacent to this angle x is 2 root 2 over 3, right? That's what you had. Perfect. Tangent, what do we got for that?
Opposite over adjacent.
TOA, opposite over adjacent. So that'd be, what'd you get?
Square root of 2 over 4.
Oh, okay. Or 1 over 2 root 2. And you rationalize the denominator just because you always had to back in the old days in pre-calc, because you could. The reason we rationalize something is to do what? Do you remember from Calc 1? Find a limit, which, yeah, could be to find a derivative. This is equivalent to square root 2 over 4. Either one of these. Biggest thing is this is not exercise number 7. We want to make sure we match the answer in the back of the book, right? All right, so C. So this is pretty easy now once you draw the triangle, right? So cotangent is 1 over tangent. So you can do it that way, or you could say it's adjacent over opposite. Either way. So who had this one? What do you got for this? 2 root 2. Okay, which I don't want square root of 8, because square root of 8 is not simplified. It has a perfect square in it. So anyway, perfect whole number square anyway. D, secant x. So secant is 1 over cosine, right? So cosine is adjacent over hypotenuse. So this is hypotenuse over adjacent. It's just the reciprocal. And who had this one? 3 over 2 root 2. Once again, if you wanted to rewrite that, that would be equivalent to 3 root 2 over 4, right? So whatever matters. you know, this first one's good enough for me, okay? On homework or something to turn in or test, stuff like that. Anyway, but just want to make sure you match the answer in the book. And then we had cosecant x, cosecant x. Cosecant is 1 over the sine. So instead of opposite over hypotenuse, it's hypotenuse over the opposite, which is what?
3.
3. So it's 1 over 1/3, which is 3. Okay, perfect. Okay, so pretty easy stuff on that, right? All right, so let's get rid of this. There was also potentially a theorem that there was a theorem that we had. Potentially you might have proved it. Do you remember what that theorem was? Had to deal with the arc cosine. Arc cosine of x plus the arc sine of x, I believe. I'm remembering it right. I can't find it, but what does this equal? Pi over 2. Pi over 2. Okay, so we had that theorem as well. All right. Let's see. Let's just look at a couple other examples here based on like those derivative theorems that we just did. If I've got y equals arc sine of x cubed plus 3x, then what's dy dx equal? First of all, you act like this is okay, right? So this is arc sine of a function. So we're just going to act like that's okay. Derivative of arc sine was 1 over square root of 1 minus x squared, but I have this thing. So it's going to be 1 over the square root of 1 minus that thing, quantity squared, right? So that's x cubed plus 3x quantity squared, but then what do I got to do since it was a function? By the chain rule, take times the derivative of what's inside, which is what? 3x squared plus 3. You know, so this is good here. Obviously, we could rewrite this a little bit simpler, and if you want to factor on top, you can. I can pull a 3 out. I'm left with x squared plus 1. Sum of 2 squares does not factor. All over, and do I need to multiply this out here? I don't really need to, do I? So x cubed plus 3x, quantity squared, 1 minus that under the radical, okay? So anyway, either one of these is correct. So, but basically I just made this like over 1 and I multiplied the numerators together and etc. So anyway, so we have that. That'd be an example. You want to do one more derivative that's maybe a little bit more involved just for fun. But if I have f of x equals arctangent of, and you got to be careful on how it's written, of the natural log of x plus 2 quantity cubed. If I have something like that, I might just, instead of having 2 parentheses here competing against each other, I might make that a bracket. So the arctangent of the bracket, inside the bracket, I got the natural log of x plus 2 quantity cubed. What might be something that you want to do here? Before you take a derivative. I want to take the derivative. And drop that 3 down. We're Where can I drop it down in front of? Down in front of the natural log. So I can put that 3 natural log of x plus 2, might make it a little bit easier when I use the chain rule, right? So use your log rule first. And of course, derivative of arctangent is, so this is just arctangent of a function, right? So I'm gonna act like it's okay. It's 1 over 1 plus that thing squared, right? So it's going to be 3 natural log of x plus 2 quantity squared, right? So 1 over 1 plus x squared, but that's my function. And then times the derivative of what's inside. So by the chain rule, what's inside is 3 natural log of x plus 2. What's the derivative of natural log of x? 1 over x, right? So, but it's an x plus 2. So it's going to be times 1, well, first of all, and then derivative of constant times a function is the constant times the derivative of the function. So it's times 3 times, and then 1 over x plus 2. But then I also got to take it times the derivative of what's inside here, because this was natural log of a function. So this is actually chain rule within the chain rule. But the nice thing is derivative of x plus 2 is 1. But if that was 5x plus 2, I'd be times 5 there, right? Makes sense? So chain rule within chain rule. And then basically what I can do is I can rewrite this, make it look a lot nicer. So the only thing on top besides 1s is a 3. When I multiply them all together, I'm going to pull that x plus 2 out in front. And I'm going to take it times the quantity of what's left, which is 1 plus. Now this is 3 natural log of x plus 2 quantity squared. I could leave it like that, or I could square out the 3 and get a 9, and then this would be natural log squared, but there's not really a simpler way to write that. So I think I'm just going to leave it as 3 natural log of x plus 2 quantity squared, which is good because you probably can't see that on the, possibly see that anyway. But anyway, so we've got this, and then once again, if it's an odd exercise, just make sure that your format matches the answer in the back of the book. What? You can't see that? I can see that. It's just this thing times 3 over x squared. Right. But anyway, got to bracket it off there. All right. So hopefully besides word problems, that's good for you there. We just got to remember some trig stuff in this chapter too. So anyway, go back and review some of the trig stuff that we did, which we did together. All right. So what I think I'm going to do is hit the highlights of section 5.8 for you. So section 5.8, we're going to undo the derivatives, and we're going to actually take antiderivatives or integrals. So we're going to do integrals involving inverse trig. Inverse trig. Functions. Okay, so those are functions. Integrals involving inverse trig functions. So the nice thing is, if we have, for example, if we have the antiderivative of 1 over the square root of 1 minus x squared with respect to x, once again, that dx could be out to the right or it could be on top, couldn't it? Because 1 times dx is dx. What do you think this is going to be? What kind of sign? Arc sign. Arc sign of x plus c, right? Don't forget your plus c. When you have a general antiderivative, we have a family, right? But long story short, you can ask yourself, if an easy question, the derivative of what is 1 over square root of 1 minus x squared? Well, the derivative of arc sign is 1 over 1 minus x squared, right? So we have this is a theorem. So as long as we know the other one to be a theorem, that the derivative of arc sine of x is 1 over square root of 1 minus x squared, then we can prove this one as well by just taking the derivative of my answer, right? So all of a sudden we get something that, because we know the derivative of arc sine is very easy, although before you looked at section 5.7, you might be like, wow, that's messed up stuff, right? But it's not really. And then what else do we have? So we can do a lot of these. If I have, let's put that minus sign on here. So if I have minus 1 over the square root of 1 minus x squared dx, the derivative of what is minus 1 over square root of 1 minus x squared? Arc cosine. So this is arc cosine of x and then plus c. So I got another question for you then. So this is also a theorem here. We have two different theorems. Do you normally see this minus sign when we're taking antiderivatives? It's not already built in there, right? So what could I do? Could I put it on this side and make that one a positive? So the derivative of arc cosine of x is minus 1 over the square root of 1 minus x squared. And then the derivative of a constant times a function is the constant times the derivative of the function. So times minus 1 would make it positive, right? Does anybody notice anything that I can do right up above there then?
Arc sine.
So this is equivalent to what? Minus arc cosine of x plus c. And you got to be careful between that minus 1 out front and the minus 1, and the exponent is the inverse cosine. So it's the antiderivative of 1 over the square root of 1 minus x squared with respect to x is arc sine of x plus c, but it's also equivalent to minus the arc cosine of x plus c. So once again, nothing hard there, but because they're so similar and they just differ by a minus sign when you take the derivative, that works out pretty nicely. Okay, so once again, if you're trying to match an answer in the back of the book, you got to really pay attention to, hey, you know, if you had something that had arc cosine in it, but they have something that has arc sine in it, doesn't mean that you're way off necessarily. Like, you just have to evaluate the process and see what they were doing there. All right, and then let's look at a couple of other ones. So a lot of times what the book will do is they'll have like a u. So it's square root of 1 over square root of 1 minus u squared du, antiderivative of that. Well, that would just be arc sine of u plus c, or minus arc cosine of u plus c. So a lot of times they're going to use a u there instead of an x. Really, it's the same variable. This is a dummy variable, whether it's an x or a u, right? A lot of times what we're doing is u is a function of x. So if we know what that function is, we're going to have to do some other manipulation there too. So what are some other antiderivative theorems that we have? I've got the antiderivative of, I'm just going to write it like this, dx over 1 plus x squared. What's this going to be? Should be pretty easy. Arctangent of x plus c. Okay, now we could actually rewrite this a little bit. What if I have, so once again, instead of putting 1 over that and then the dx out front, I just put the dx on top, right? Everybody okay with that? But instead of having a 1 there, what if I had an a squared? So if a is some element of the real numbers, so a is a real number constant, and I square it plus x squared, what do you think that's going to end up being? It should end up being something like this, right? Something like arctangent. Okay. So It is. It's actually going to equal 1 over a, which is a constant, right, times the arctangent of x over a plus c. Okay? Now, we can prove this by taking the derivative of the right side, or we could use substitution. What do you prefer? Like, I could try and make this side look like it's arctangent, but how about we just verify this? Anyway, but these are two theorems here. So this is the easy one, right? It matches it where it's just a 1. But this is the one that you want to know here. Why? Because if a is a 1, what does this become? This is just 1 over 1, which is 1. Arctangent of x over 1 is just arctangent of x plus c, right? So we get that. But let's take the derivative of this side and see if we get 1 over a squared plus x squared. So derivative with respect to x. Remember, a is a constant. So derivative of a constant times a function is the constant times the derivative of the function. So that's just 1 over a. And then the derivative of arctangent is what? It's 1 over 1 plus that thing squared. That thing is x over a. So it's 1 over 1 plus x over a quantity squared times the derivative of that thing. Well, that's like 1 over a times x, right? So the derivative of a constant times x is just a constant, so times 1 over a. Well, what do you notice here? So that's a chain rule here. But what do you notice? 1 over a times 1 over a is 1 over a squared. And then I'm multiplying that times what I got here, which is 1 over 1 plus. I'm going to square out the x over a quantity squared is x squared over a squared. Right? Now, if I've got 1 over a squared times that, then basically I can just multiply 1 times 1 and I get 1. And then a squared, I'm going to multiply through the denominator, and what I get a squared plus, and then the a squareds cancel. So I'm just left with x squared. So I get 1 over a squared plus x squared, which is exactly what I had over there. So there's your proof of that theorem based on knowing the derivative from section 5.7. Okay? So we have, the easy inverse function here, antiderivative. That's pretty easy to do, but we've got some here where we've got some constants to deal with to pay attention to as well. So let's look at a couple other of these. So if I have So let's go back to the one that we had for arcsine. Could I do something similar where I have 1 over the square root instead of 1 minus x squared, call it a squared minus x squared? By the way, a squared doesn't have to be a perfect square. I know we got to get going. So this could be a 5. So what would a be? A would just be the square root of 5, right? All right, but anyway, so if I have this with respect to x, just real quick, write these up, and then I'll finish up here. We've got, this is arcsine. By the way, there's no 1 over a factor in front here. This is arcsine of x over a plus c. But it's also equivalent to minus the arc cosine of x over a plus c. Now I'm going to let you take the derivative of the right side, but I do want you to note there is no 1 over a factor in front for the antiderivative on this, like there was on the arctangent. Okay, and you'll verify that if you take the derivative of the right side. And then just real quick, we had the antiderivative 1 over a squared plus x squared. This is 1 over a arctangent of x over a, but what else could it equal? And then plus c. This is also equivalent to minus 1 over a arc cotangent of x over a, and then plus c, right? Because the derivative of, excuse me, I missed my arc tangent. Got to make sure I have that minus 1. That was a big mistake there. 1 over a arc tangent of x over a plus c is equivalent to minus 1 over a arc cotangent of x over a plus c. Because if I take the derivative of this one, it's the opposite of arctangent. Okay, and then a couple of more, just the last two, deal with arc cosecant. So the antiderivative and arc secant, the antiderivative, excuse me, which one's going to give me arc secant? If I have dx over x times the square root of x squared plus a squared. Okay, that looks like arc secant. Okay, but once again, here I have the 1 over a factor in front, the x over a here, and then plus c. Okay, so I do have that 1 over a factor for this one. And then, of course, this is also equivalent to minus 1 over a arc cosecant of x over a plus c. Okay, just because of the way those derivatives work. So the only one that doesn't have the 1 over a factor in front is the arc sine and arc cosine. Otherwise, we have those. All right, so anyway, that's good for today. Thanks.